In this video, we are going to review some basic principles of kinetics. So let's start by thinking about this thermodynamics graph we looked at. So we have our free energy, we have our reaction coordinate, we have reactants, we have products, and then we saw this kind of hill, that energy barrier. Right? And the height of that hill, how much of an energy barrier there is why different reactions take a different amount of time. So that hill is the reason for the different speed of reactions. Okay, we're going to review some here. If you run a reaction, we can, in the lab, run a reaction and measure either the concentration of the reactant, which will be going down over the course of the reaction, or the concentration of the product versus time, whichever is easier for us to measure. We can determine a reaction rate. Okay, so we're talking about the speed. In biochemistry, we tend to call this the velocity of the reaction, the speed of the reaction. It's the same thing as the reaction rate. Look at our units. Products over time, we're going to be talking about some units of concentration over some units of time. Molarity per second is a common one. And then we can propose a rate law. Okay, so rate equals K. We've got this proportionality constant right here. And right now, this would be experimentally determined. Experimentally determined. That is very messy, but you get the idea. And that is not that proportionality constant. Okay, this value, X, cannot be determined just from the chemical reaction, but it can be determined from our experiment. And if you remember from Gen Chem, we talked about method of initial rates, and we actually figured those out. But let's think more about it just in general. If you run reactions with different initial concentrations, we can look and see how the rate changes. So for now, we're going to assume we have just one reactant. If we change the reactant concentration and we see no change, we're going to say that the order with respect to that reactant is 0, that the concentration of the reactant did not matter for the reaction rate. On the other hand, if we see a linear change, okay, as we double the initial concentration, we see the reaction rate double, we're going to say that's first order. And if we see an exponential factor, we're going to say that's usually second order. It can be higher order, but this is the most common, is 0, 1, and 2. All right, if we look at one possible experiment over here, this would be an example of a first order experiment. As I increased the concentration, we see that change. If I wanted to look at a 0 order experiment, so I've got time, I've got concentration on my product, and let's say that first reaction, the one shown in red, gives me some amount of product per time. And then I change that initial concentration to the one shown in green. You know what? For a 0 order reaction, we'd see that exact same line. And then if I changed it again to the one shown in blue, I would again see the same line. So this would be a 0 order reaction. All right, so that was for a unimolecular reaction. Let's talk about bimolecular reactions, which are very common in biochemistry. So in a bimolecular reaction, we'd have 2 molecules interacting to go to our product or products. If these are a single step, if they're a single step, we can write our rate law. So remember, rate can also be called velocity. It'd have some proportionality constant, and in this case, it'd be R times R, or better yet, K R squared. It would be second order in R. Over here on the right, we'd have some different proportionality constant. We'd have one reactant to the first power, the second reactant to the first power. So it would be first order in reactant 1, first order in reactant 2, and second order overall. We sum those up. We can figure out these exponents. Okay, so the exponents here, these are understood ones. We can figure those out from the coefficients in the equation if it is a single step. So in a reaction mechanism, each step is a single step, so we can figure those out. All right, so it turns out in biochemistry, when we do a bunch of the experiments that we expect to be second order, they appear to be first order. And you might remember from general chemistry, we talked about pseudo first order reactions. All right, here, I'll write that. Pseudo first order. And in Gen Chem, when we talked about that, let's look at this one over here. We talked about a situation where we've got a whole lot more of one reactant than the other. A lot more. So if we use up, say, half of the first reactant, essentially the concentration of the second reactant is barely changed. Maybe we had half a mole of the first reactant and we've got like 1,000 moles of the second reactant. Well, if you use up all half mole, you've still got 999.5 moles. It's barely changed. So in that case, reactant 1 would look like it's controlling the entire rate. Okay, so in biochemistry now, what we're going to see is that because these enzyme-mediated reactions have different mechanisms, it's also often going to be this pseudo first-order appearance. Let's take a look at this. Now, first of all, I want to point out here, you remember we said rate could be called velocity. Well, you know what? When we talk about reactants, we're often going to call them substrates, if I can spell substrates. So when you see that S, it's talking about the reactant, okay? If I look at this, we have these hyperbolic curves, these enzyme-mediated catalysis. If you remember the curves we looked at before, this looks like that. When I look, if I had some concentration of my substrate, my reactant, maybe S1, I change it, I get a different curve. I change it again, I get a different curve, S3, and so forth. And if I kept going, maybe I change it again and I get a little bit different curve. But what I start to see is these curves start to close in on each other and become barely different. And if we now change, and instead of putting time here, we put substrate concentration, what we get is this curve, okay, that starts to reach this maximal velocity. It starts to level off up here. Okay, the substrate concentration is changing, but the enzyme concentration is going to be constant. We're going to hold that constant in this case. All right, that is your review of kinetics. Next, we'll talk about kinetics specific to the enzymes.